Now let's see if we can figure out the mystery of the complex numbers in our family of solution here. I said that we can expand the exponential terms using the Euler's formula. Let me just bring it up again. So as a reminder, Euler's formula told us that e to the power I theta, or whatever it is, multiplied by I, is equal to cosine theta plus I sine theta. Okay, I'm just going to insert whatever we had in this formula and expand the exponential term by these two cosine and sines. Okay, so let me do it right away. Oh, sorry. Okay, so just inserting one by one, I'm just going to write out the equations one below the other. So f is equal to, let's start with the first term, c1 e to the power beta times 1 plus I. Okay, so if you can remember, if you have an exponential and you have it to the power something plus something else, you can write it as multiplication of the other one another. So for instance here, you can write, let me write here, I want to screw my beautiful blank piece of paper. So e to the power 1 plus I would be equal to e to the power 1 times e to the power I. I hope you can remember this guy. So I'm going to use the same thing. So C1 goes here. C1 is alright, it goes here. Times e to the power beta, I can write it out. And then multiply it by e to the power I beta. Okay? But e to the power I beta, that's the thing I want to expand with Euler's formula. So I'll write it as follows. I would say it's equal to cosine of beta. Oh, by the way, I forgot all the x's here. Sorry. I mean, there's going to be an x up in the exponents everywhere. Okay. So we'll have. So let's start again. I had e to the power beta times e to the power I beta x, and there's the x here too. The one with the imaginary number in the exponent, I can write out with the Euler's formula. So I'll have cosine of beta x plus I sine beta x. Okay, I could do that with it. That's pretty alright. Okay, now let me write out the rest of them too. Just going to write out the next guy. It's everything just identical to this except for that it has a minus sign beforehand. So I would say it's equal to C2 times e to the power, it had a minus sign, so minus beta x times, okay, so it had a minus here. Cosine of minus something is equal to cosine of that thing. So it doesn't make sense to put a minus sign anywhere here. So just say cosine of beta x, right? And sine of a minus is minus of sine of that thing. So it's minus I sine beta x. I hope that you're comfortable with what I did here. I had a minus here in the middle and said the cosine of a minus is cosine of that thing. So it doesn't change, the sign doesn't change. But a sinusoidal function is different. If I have a minus in the middle, if I want to take it out, I should really put out. The sign would change. Okay. So let me do the other ones. Let me do the C3. C3 had a minus 1 plus I. So I'm just going to write it out. Plus C3 times, it had a minus 1, so e to the power minus beta x, right? but it had a plus I x, so it's just going to be identical to what I wrote here. Cosine of beta x plus I sine of beta x. And then I have the fourth guy too. The fourth guy was just this one, except for it was multiplied by a minus. So e to the power beta x, I'm just going to write it fast. Would have cosine of beta x minus I sine of beta x. Yeah, hope I wrote out everything correctly. I hope so. Okay. So now let's see. Let's put everything together. I had some places where there were e to the power beta x, so let me factor them out, and e to the power minus beta x, I'm going to factor them out too. So this is equal to e to the power beta x times what we had here, we had c1 times the cosine plus I sine. And here I had c4 times cosine minus I sine. So let me see if I can write everything out in a compact form right away. So I had here c1 times cosine and c4 times cosine. So let me take the factor out the cosine too right away. So I'll say c1 plus c4 times cosine of beta x. Oops. Okay. And what about the sine? That was the same story, so I would essentially have plus c1 minus c4 this time, because it was a plus here, so there's a minus here, so c1 minus c4 times, then the sines, I just factor them out, so it's sine of beta x. Okay, so that was the e to the power beta x, and I had minus beta x too, so I gotta do something about them too. And I will have plus e to the power minus beta x times, what am I going to have here? Squeeze this guy in. Alright. So I'm going to factor them out on fly too. So you see we have cosines here, so I'm going to factor them out. Everything in here are going to be added up together with multiplication c1, c2, and c3. So I'm going to factor out the cosines, so they're multiplied by c2 and c3, so those guys, I can write out c2 plus c3 times cosine of beta x. And then I can write out, oh, by the way, I forgot the I here. There was an I here that I forgot. When I was factoring out sines, I forgot to write out the I. So there is I here too. Plus I times minus c2 plus c3 times sine of beta x. Okay, please do that yourself once, just to make sure that I did everything right. But hopefully we got it right this time. Okay, now let's take a look at it. The i's are still in here, the imaginary part. So this is like this thing in here is essentially a complex number. So this is the real part of the complex number, this guy here, and this is the imaginary part of the complex number. But why the hell, we didn't have any imaginary numbers anywhere, so why this thing is here? So you see, this was a contradiction. We didn't have imaginary numbers anywhere, so we shouldn't our differential equation was, everything about it was real. So the solution to that should be real too. Therefore, we can conclude, we have to conclude that it's the only way, that I times this fellow in here is not imaginary. Okay, what the hell? I'm telling you guys that I times C1 minus C4, by the way, we didn't know what C1 and C4 are yet, but I'm just going to tell you that this guy is equal to a real number. That's the only way this whole thing makes sense, because otherwise, if it's equal, if this guy is imaginary, then I'll have imaginary numbers everywhere and complex numbers everywhere. So that's the only way to go. This guy has to be real. But how come this? How can we make this guy real? I mean, this guy, how could it be real? It has an imaginary number here. So what if this C1 minus C4 is also imaginary? So this guy is like, I don't know, something, I would say E times I. Then the i's get multiplied to one another, and I'll have minus E. And this guy would be real. That's the only way it makes sense. Okay? So, but the bottom line is that I times C1 minus C4 has to be real. Okay, and the way that it could be real, I just explained it, that C1 minus C4 is imaginary, therefore imaginary times imaginary, I will have a real number. Okay, so now let's do something. Let's compact everything down. Let me write out, instead of C1 plus C4, let me write one constant like D, so that everything is neater. I'll write everything down here. F is equal to e to the power beta x times, instead of C1 plus C4, I'll write D1 cosine beta x, and I times C1 minus C4, we just argued that it has to be a real number, so this could also be a D2 times sine beta x. Okay, that was all about here. And we have another term here. In this term also, minus C2 plus C3 times I has to be real. So minus C2 plus C3 is imaginary, multiplied by I, we will have a real number. So let me write out here, let me make the constants compact too. I'll say plus e to the power minus beta x times d3 cosine of beta x. So d3 stands for c2 plus c3 plus d4 times sine beta x. And d4 is real because I times minus c2 plus c3 was real. Okay, so right now we let go of the constants with c, so we don't need them anymore, and we have these instead. And the task is to find the constants d, and then we will have the solution. But up until here, we have the family of solution. That's pretty neat. Right here. And what is more, previously we had complex numbers everywhere. But we saw that that was not that was a false signal. I mean, they were not actually complex number. Everything was real, and everything had to be real, because if once you start with real numbers, you have to end up with real numbers. Imaginary numbers don't come out from sky. Okay, so that's the family of solution. I would like to leave finding the constants, these, up to you. But there's one boundary condition here that I just cannot resist not solving, not paying attention to it. Let me find where